Yep, you called it, Abdul. Also, the chat is not functioning again because I don't ever fix anything. One of these days. Let me fix that. There we go. This is a weird problem. It took me a while to kind of figure out how to read it. Thanks for the heads up on the meeting. Jeez. I barely missed you on this one. I tried to watch the stream live, but it looked like I missed you by like 20 minutes. Watched a few minutes, but I didn't want to watch it before I solved it. I'm glad to see you're keeping it going. So I'm trying to figure out what this problem is like. It definitely reminds me of a graph. So I kind of want to take these things in. It's basically like an adjacency list. So 1 trust 3, 2 trust 3. So, thinking, what does this look like? It reminds me of some things. It's kind of tickling my brain a little bit. I'm almost thinking like let's take an example here. So if we were to come in here, and we got this tree, or not tree, we have this graph. So if we had an adjacency list, it would look like this. 1 points to 3, 2 points to 3, and 3 points to 1. So after I figured this out, then I could go through each one of these and say, well, I only want to look at the ones that don't trust anyone. So maybe if it looked like this, then I could go here and say, hey, 3 is a contender, but I need an easy way of knowing how to get back to everyone that trusts me. So what if I did it backwards? What if I started here and they tell me 1 trusts 3. So I said, hey, 3 is trusted by 1. Then when we get to 2, we say, hey, 3 is trusted by 2. And if that was it, then I would know that there aren't enough keys in my map here. So I would know that So if this was all I had left, then I could see that there's only 1 key that is trusted by n-1. So that seems like a winning strategy. Let's try a bigger one. All right. So here, I would say that 3 is trusted by 1, 4 is trusted by 1, 3 is trusted by 2, 4 is trusted by 2, which I already have, and 4 is trusted by 3. And here I can see that there is 1 person that is trusted by n-1. Okay, and so in order to avoid kind of looping through my list here and looking for the count, I guess I could probably keep track of who my winner is the first time I see him. And if I see more than 2 judges, then I can return -1. So, okay. So just kind of high level, what we're going to do is loop through trust, store, adjacency, list by whoever is trusted. If the list length is, did I build that right? I don't know. Let's try it again. So what I'm kind of doing is I'm keying by the value instead of the person. So I say person 3 is trusted by 1, person 4 is trusted by 1, person 3 is trusted by 2, so I probably didn't do it right. Person 4 is trusted by 2, and person 4 is trusted by 3. this is the only person that has the correct length. So that's my only judge. So we can return 4. Is that the right answer? What? Output should have been 3 though. What? Yeah, I got the wrong answer here. What did I do wrong there? This is the person who is trusted. Whoa. Oh, wow. Yeah, good call. Okay, so 3, I'm going to do it one more time. 3 is trusted by 1. 4 is trusted by 1. 3 is trusted by 2. 4 is trusted by 2. 3 is trusted by 4. Okay, yeah, good call. So the algorithm is still good, and I am not a good computer. All right. So loop through the trust, store adjacency list by trust. I wonder if they ever give us duplicates. If they don't give us duplicates, we could just keep the count. Let's see. They tell us anything about that? Less than 1,000. Trusted I are all different. Trusted I at 0 is never equal to trusted I at 1. Okay. I don't know about that. I would rather be a computer. Yeah, so let's see. Let's take a look at this again. So 3 is trusted by 1 person. 4 is trusted by 1 person. 3 is trusted by 2 people. 4 is trusted by 2 people. 3 is trusted by 3 people. Can we just keep the count? Can we skip the list? That's fine. Trust.length, don't care. Trust at I are all different. So no duplicates. Okay, good. Trust at I at 0 is never equal to trust at I of 1. What does that mean? Trust at I of 0. Oh, they never trust themselves. Okay, yeah, so this, we could totally just keep the count, but missing another check. Yeah, I have to worry about the case where there's 2 judges. Just return -1. And if there is no key with enough, am I still missing a check? Loop through the thing, store adjacency count by trusted. If the list length is n-1, store as judge. If we see 2 judges, -1. I think they actually said there's exactly 1 person that satisfies 1 and 2. So I don't think we have to even really worry about the fact that there might be 2 town judges. I mean, I don't think there could be 2 town judges. Yeah, I don't think we have to worry about that. I don't know, we'll see. Find the which, hey, what's up, Abhishek? Find the which is not int, trust I at 0. Find which is not I at 0. So some number, so one of these, oh, wow, that's slick. So you could just loop through this list and find whichever number is never in the first position. So in this case, we could have said 4 isn't here, 4 isn't here, 4 isn't here, 4 isn't here, 4 isn't there. So we would know that. So yeah, another way of saying this is that I exists. So my number, so we'll say this never exists. Never exists, but 0 ... you know, everything but and does exist. Which means that I've got enough values here. I don't know, you tell me, am I understanding correctly? So what's another, how would I write this? So I loop through and I see that 1 is in the left, which means that 1 can never be our answer. We see a vote for 3. How do I store that 3? Or how do I know that I've seen that value for 3? Here, I see that X is potentially the is not the answer. So if I loop through all these, then I can see that the only numbers that could be our judge are 3 and 4. It's not 3 though, because not enough people trust 3. Or no, I keep saying that wrong. Not enough people trust 4. Oh, but they're okay. I see. So if we look back at these examples, here I can see that 2 never trusts anyone. They must be the judge. 3 never trusts anybody. They must be the judge. Here, 3 trusts somebody. They can't be the judge. So nobody can be the judge here. Example 4. N equals 3. So 1 can't be the judge, 2 can't be the judge, but 3 can't be the judge either because we haven't seen enough of these. Okay. Potential is only 3. So I think I still have to keep track of, because I have to worry about this case here. Am I missing something? I think I have to keep the counts per key, per person. So I think I have to do it this way. I could be wrong though. Huh. Let's take this over into Kotlin. Kotlin IntelliJ. Example number 4 is given wrong. Let's see. In a town, it's possible for there not to be a judge, as if the town judge exists. So it will be if the town judge exists and can be identified, return the label of the town judge, otherwise -1. And down here, we know that there are no duplicates, and no person ever trusts themselves. Okay. Hey, what's up, Vlados? Hope you're having a good one. Man, I showed my wife pictures of Kotor, and now she wants to move there. This is beautiful. Let's see here. What was this one called? Learned this insert, this shortcut yesterday. Control Shift Insert. Nope. Control Insert. Control Shift I. Oh man, I looked up the shortcut in IntelliJ for creating a new file, and then I forgot it. There we go. Control Alt Insert. And this is going to be test, judge test. Yeah, I would love to visit Europe again. I'm not a big traveler, but man, seeing pictures like that, the mountains and the water, like sold. All right, so we got, copy this. Okay, and this one looks pretty good. So we do need a map of, what do we want to call it? Let's see. It's a map of trust counts. So we'll call it trust counts. And that equals a map of, a mutable map. Hey, the visit? Desert in the summer? I don't know. I might have a harder time with that. Oh, cool. How'd you think about doing it? Yeah, I don't know about the desert. Although it'd be great for allergies. mutable map of, and we've got ints and ints. Why don't you like this? Why is it yelling at me? Oh, I think mutable map is the interface. Hash map. So I can just do hash map, that's fine. And we're gonna loop through trust for each. Which means we could also do a fold. Well, I don't, yeah, we'll do a fold. We'll initialize with this. That way we don't have to think of a name for it. Oh, you're talking about the oh yeah, the next square one. Yeah, that was really cool. Oh, gotcha. So yeah, rather than, yeah, doing the kind of like the looking for prime numbers kind of, or, Gotcha. Yeah, I think I know what you're talking about, like all prime numbers or the form 2n plus 1 or 2n plus 2, something like that. I forget. Let's see. Why is it yelling at me again? Okay. So fold cannot be applied to. Oh yeah, I need to tell it. Yeah, primes are funky. It's been a while since I've had to mess with primes, since I did a Project Euler a couple years ago. Pronounced it correctly for once. Yay, first time. So here I'll say the hash at our value I. And I'm not going to name it I. I'm going to call this, I don't know, trust map or something. So trust map at 1 is the person who is trusted. Plus plus, and I don't even care. Oops. Equals plus 1. This is possible to be null. So I could say like set or default. R equals yeah, let's do it like this. The key is going to be trust map at I, or at 1. Yep. Yeah, that's right. 6n plus minus 1. Yeah, that's the deal with primes, is that they're hard to predict, but there's like a pattern where primes are, they eventually get to, let's see, prime calculation 6n plus 1. They eventually fall into a pattern. Whoa, which is over my head. I can't explain why. But when you're looking for primes, you eventually get to a point where you don't have to check every individual increment. You only have to, yeah, check 6n plus 1 or something. 6n plus 1 and 6n minus 1. That's it. And so it may not be 6n plus 1 or 6n minus 1, but all primes eventually fit this pattern, which is strange. And it looks like there's some good answers behind why that is. I've read on it before, I don't remember, but it's, I don't know. It looks like a complicated reason why that is, but it's pretty cool. So when it comes to calculating primes, there's a couple different popular methods. There's the sieve of Erasmus or whatever. Erasthenes. But I've never really programmed it that way, where you kind of like cancel out all the 2's and then cancel out all the ones divisible by 3 and so on, and eventually you get to a good spot. But the way I've done it before is basically by, it's like a couple different things. Let me see here. Josek Ruby prime generator. Many years ago, what year is this? 2010. So 10 years ago, I was messing around with prime numbers, and here's how I ended up doing it. And I don't remember if this was good or not. I did it in Ruby. And yeah, I don't really remember how to read this, but you would basically, if you're trying to figure out if a number was prime, I would build it up with a prime generator, and then for any given number, I would check to see if it was divisible by all prime numbers before it. But you only had to check up to the square root of that number. So if you're checking to see if 15 is prime, then you only have to check 1, 2, and 3 to see if it's prime or not, which is pretty cool. And so this used memoization. So anyway, I just remembered this was being kind of a cool way of doing it. And then looked like I would check n plus or minus 4 or 2. I don't know why I didn't do 6n minus 1 or plus 1. So, but yeah, there's a couple tricks here, like checking only up to the square root of the number, and then the 6n plus 1 or minus 1 trick is nice. Hey, my cert's invalid. All right, anyway. Fun times. 10 years ago, and I don't remember how to do it anymore. Awesome. All right, so this is trust. No, it's hash.get or default of our key plus 1. Get or default should have been 0. Okay, plus 1. So basically, every time we see an item, we'll store it in a hash, and then I think we have to return the hash. Is that right? Okay, so this loops through and it keeps an adjacency count. So we got that, and then we could do some shortcuts here. Yeah, so the 6n trick is, yeah, I remember something. I don't remember all the details, but I remember it being kind of like a nice trick for speeding up the algorithm that was just kind of funky. Yeah, I'm all about the derailments. I like it. It's fun. So should be replaced with indexing. Okay. Yeah, it looks a little nicer. So here we're doing this kind of thing. Now we do have the potential case where, let's say we have val judge equals -1, and we'll return the judge. Okay, and then here, if hash at trust map equal at 1, if that, no, sorry, if hash at trust map 1, that's right. If it equals n minus 1, then we found our judge, so we can return our judge, because they said there would never be more than one judge. There's at most 1, so we can just return trust map at 1. And here we don't need to keep anything, then we could just do -1. I think that's good. If the list is n minus 1, then there we go. If there is no key with enough numbers, then we're good. All right. Let's see, maybe we can skip writing the tests. What could go wrong? Just try it. Got the right answer. How's the runtime? We do look at it's order n. We don't allocate any. Oh, we do allocate up to n. So the space complexity is not great. Oh yeah, this problem. So this problem, we have an array of numbers, and we're looking to see if one of the numbers is the town judge. And the town judge has some special rules. They trust nobody, and everybody trusts them. And there is at most one judge. So we get an array that says this person trusts that person, this person trusts that person. So we need to figure out, it's basically a graph, and we need to find a node that links to nobody, but everybody links to it. So we started kind of saying like, oh, we'll just go through and keep an adjacency list. So what that looks like is here 1 trusts 3, but we said if we reversed it and say 3 is trusted by 1, and we go to the next value, 3 is trusted by 2, so we can add 2. And here 1 is trusted by 3. Then here we can see that person 3 is trusted by every other person, 1 and 2. And do we know that it trusts no one? So yeah, there's one other condition I think, Abdul, I think you mentioned, which is we have to check to make sure that 3 never trusted anyone. And did I not account for that? This might be a flaw in my logic. So it's possible to have a number where I say, you know, 1, 2, 3. Yeah, actually, this is a perfect example where 1 trusts 3, 2 trusts 3, and 3 trusts 1. So this is a case, actually, this particular example that I grabbed shows the flaw in my algorithm, because 3 is an invalid judge. So I can't just return when I see it. Hey, what's up, Zach? Yeah, I need to check to see if the judge I've identified has the key in the trust map. But the way I did it, I've got the judges, the potential judges as the keys, so I can't just look up to see if, I don't have an easy way of seeing, hey, what is 3 linked to? So what's another way of storing that? If I treated this like a graph, say 3 is the key, and it's trusted by 1. I guess I could store like a node here. So instead of just the value, I also know it's, let's say like its count is 1 and what? So I guess like in here, I could say your count, or your trusted count, number of people you're trusted by, is 0, and your trust count is 1. Yeah, I thought about the list. It just seemed kind of yucky to store that extra space, and it doesn't affect the complexity, so it's totally doable. Let's see. So what if we did it this way? So we're going to store 2 numbers. We see 1. So we know, like, the original thing was we said, okay, 3 is trusted by 1, and the trust is 0, or trusts is 0. We get to 2, and we say, okay, 3 is trusted by 2. It still trusts nobody. And we get to the third element, we see 1 is trusted by 3. And if I had done this correctly, let me start over. Oh my gosh, sorry. So key. So here we're going to do 2 keys. So 1, its trusts goes up to 1, which I guess that could even be just a Boolean. So it trusts somebody, and trusted by doesn't even matter. A set for all the unique trusts, and then only keep keys at your hashpad map for elements that aren't in the set. Yeah, so I could pre-initialize. Yeah, totally. Yeah, that would work, and basically then remove the keys and only update them if the key still exists. Yeah, totally. Yeah, let's do it that way. That sounds like fun. Oh, worst case scenario there, we're allocating more than we need to, but it's still in space, and so it would only help. It would only be a hindrance in some certain situations, which I'm sure is more than adequate. More than adequate. So what we'll do is here, our hash map is pre-initialized. So we'll say, I don't know, call it maybe potential judges. Or, I don't know, trust map equals a hash map. And what's the easiest way to initialize this? Let I equal 0. So like n dot times. Hey, cool. No, that's not what I want. For each 0 dot dot n. I guess there is no 0, just 1 dot for each. Trust map at, let's see, val I n, something like this. I forget how to do the ranges in Kotlin. I think this will work. It shouldn't be parentheses, though. That's what was tripping me up. So lambda, and should have trust map at it, which is the default iterator, equals 0. Okay, so then down here we don't need a fold anymore. We just need a for each. Yeah, trust is here, so trust.forEach. Oh, and Zach, yeah, you mentioned a set, but I kind of did it as like a hash map because I figured we'd keep the counts in there too. Why don't you like this? Type inference fails. There we go. Okay. So now we just have our iterator, and we can say trust map at it. Oh, hang on a sec. All right, and I got to speed it up because I'm about to leave the house. Okay, so trust map at our value is going to equal whatever that value is plus 1. And the trick is, though, we only need to do this if it actually exists. So we will only do this if that item still exists in the trust map. Dot contains key it at 1. So if it exists, then we'll increment it. So that takes care of the value. And we can do this, we can keep this check. So basically, if our trust map, why is this so messy, at our item, then we can return our trust map at it at 1. Okay, and I'm still missing something. So if we contain the key, that's the only time we need to do this. I'm getting tripped up by this, so I'm going to just keep a variable here. Ooh. Val key equals. We'll replace. Ooh, whoa! Replace this. All right. Now we do have to do one other thing. So if trust map contains the key, hey, it didn't replace all. How come it didn't replace this? All right, don't know what happened there. Ah, I missed a parenthesis. That's what happened. Okay. So the other thing we have to do is basically is remove trust map dot remove it at 0. How is that going to error out? Is there like a remove if exists? Let's see. Whoa. Remove return this dot remove node, and so it looks like it'll return whether or not it actually removes it. So I don't think we have to do it. So is one dot dot n inclusive of n in Kotlin? I don't know. I assumed it was. Let's see. In range. For I in 1.4, we'll do I less than or equal to. So yeah, that is inclusive. So I believe that's good. All right. Now I made a lot of changes here, so the chances of this working off the bat are slim to none. Ozak, you'll be proud to know that I do use VI quite a bit more. I still don't do a lot with it. Oh my gosh, wrong answer. But it's everything you showed me has been really helpful. I particularly use the word stuff a lot. The W. Surrounded by. So I got the exact wrong answer. So what happened here? I took in a 1 and a 2. I should have removed the 1, so it's not a potential answer. It's initialized to 0. So I set my key. I removed from our trust map and IT in 0. So we removed the 1. And it only passed this. Trust map removed the 1. And we said if it contains the 2, trust map at 2 equals trust map at 2 plus 1. If trust map at 2 is equal to 1, then, oh, I returned trust map. So I'm returning the count. And I should have returned the key. Yep, you called it. Good call. Seems to be running slow, but I think it's a good algorithm. All right, there we go. So because I'm late and my wife's going to beat me up, I'm going to see if the submit works. Wrong answer. Uh-oh. I'm in trouble. So should have given negative 1 here. So what happened? So it came in, I said, okay, 1 is not a contender. 3's count goes up to 1. Here, 2 is not a contender. 3's count goes up to 1. Here it should have said 3 is not a contender. So I should have said, hey, remove 3 as a possible option. Remove 3 as a possible option. And then if it contains key, don't think you ever hit the last list. Oh. Trust for each. I return in the second element. Oh, good call. Man, good call. Okay. Yep, good call. I can't exit early. Good call. Okay. Wow. All right, so over here, this needs to be return key now, but this whole condition is false. So one way to do it would just be to loop through trust map and look for the right count. And I think that's pretty good. Yeah. The candidate screwed it up, man. Okay. So, in the interest of my wife not murdering me, I'm just going to loop here. No, for each. Sure. And that will give us a map entry. So we can just say, I don't know, something like kv dot value equals n minus 1. Here we can say if the key value equals n minus 1, then we can turn kv dot key. Otherwise, -1. Oh, no way, man. This is it. No more bugs. Pointless. This is coding. Nah, she's still getting ready. Hopefully she can't hear this, but she's late all the time, and I'm like never late. So I think I got a little room here. Got the right answer. Come on, come on. All right. Okay, I'm going to quickly look at more details. Solidly in the middle. Just going to quickly look at the best answer. Yeah, this is being recorded. Yeah, I'm always in trouble, but I cook really well. So I think I can get her back. I got steaks for tonight, so we'll be all right. So here they loop through and they keep... Oh, look at that. They decrement the trust counts for the key. That's cool. And then they increment the trust value and then they look over. So that's cool. So that keeps them having pre-initialized, but really this is a much faster than the solution we came up with. So that's cool. It's just trimmed down a little bit. So, all right. So I'm going to go hop in the shower. Thank you very much for all the help. That was awesome. It's good to see you.